All right, we are here in the notes, and so today's lesson is going to be you guys following along with me and finishing the notes. You guys can go as fast or as slow as you want. You can pause the video if you're feeling stuck. So let's get going. Can't do that. Okay, what we're going to do is start off by adding these vectors. Like I said last time, we are going to do tip to tail. Okay, that's how we draw the vectors, and we just draw them one at a time. So the first one in red is 3 meters west. So we have to pick a starting point. So let's say it's that. That's the start. Okay, so if this is the starting point, then we go 3 meters to the west, draw something like that. That's west. And if you write down the 3.0 meters, then that's what it is. That was 3 meters. And now, excuse me, that's some nuts, and they are flaky in my throat. Okay, then we got to do 6 meters south. I'll do that in green. And so we have to start at the tip of the last vector, and that's the tail of the new one. And so we go down here, and I try to make it about twice as long as a 3 because it's 6. And so there we go. That was south, and I put the 6.0 meters here, and that was 6 meters south. And then lastly, we've got to do the 4 meters, 32 degrees east of north. And so we're going to start here at the end of the last vector, and north would be straight up, but we're not going north, we're going 32 degrees east of that. So of north, we're going 32 degrees to the east, and so it'd be something like that, probably more, but do 4 meters, so that looks pretty good right there, and I'll mark this as 32 degrees and 4.0 meters. All right, very good. Now, what are we trying to do? We're supposed to add these three. Did we add them? Is this what we did? Well, kind of. We're on the starting point. This will help us to conceptualize because what we're trying to find is if we add these three vectors, where are we compared to where we started? Okay, well, compared to where we started, we are a little bit down and a little bit to the left or to the west. Okay, and so but that's not how we would draw a vector. We would be exactly right there. So how do we describe this blue line precisely? We need to know exactly what the length is. Let's call it R for the resultant. Okay. And we need to know what this angle is. We need to be able to describe the angle. So you can probably start to see this is going to be a party. This is going to be a lot of fun. And so to figure this out, we got to know, essentially, we got to know how far this side is and how far up and down we went. Okay, how far to the west and how far to the south. If we can figure that out, then we can use Pythagorean theorem to find r, and we can use SOHCAHTOA, tan precisely, to find theta. No problem. So how far to the left did we go? How far west? Well, what are some things we can see? We definitely went less than 3 meters, right? By our drawing, we can guarantee that. And we did go west though, right? And so this is where if you drew a terrible drawing, then you're going to have a tough time predicting, but the math should still work out. And so what I'm going to do is I'm going to, we did less than 3. How much less than 3? Well, if we wanted to really get intricate, we could say exactly this much. Well, I wanted purple. Exactly this much less than 3, right? We went 3 meters west, and then we went south, and that had no effect on how far west we went. But then we went at this weird angle, and there's this x component, so let's call it x1, and that's how far east we went. And that would we take it away, and then we can figure out this number. All right, so let's figure out what x1 is. X1. Find that. What we're going to do is we use SOHCAHTOA. So let's think about it for a second. This side is the opposite, right? And this side is the hypotenuse. And so what are we going to use? We want the opposite. We have this hypotenuse of this angle, so you're going to use SOHCAHTOA. And so let's do it. We got the sine of our angle, which is 32. There we go. equals this opposite, which is x1, over the hypotenuse, which is 4.0. Right, so if we keep going with this, we're going to multiply both sides by 4, so we got 4.0 times sine 32. That's how we get rid of that 4, and that's going to equal x1. And so our final answer there is x1 equals 1.9. And that is meters. All right, sweet. And so we found that x1 is 1.9, which means the reason we found that is that means that this value here, yikes, this is tight stuff here. This value there is going to be 3.0. Yikes, my writing is so messy. This here is going to be 3.0 minus 1.9, and that equals 1.1. Good? Oh, you might be thinking, Mr. Reimer, was your calculator in the right mode? No, it wasn't. And so I'm just going to redo that. 4 sine 32 is 2.1. Okay, weird. And so this should have been a 2.1. You can rest easy. You're not doing it wrong. I was. 2.1. And so this should be 3 times or minus 2.1 equals 0.9. That's better. 0.9. Very good. So there we go, meters. Yeah. And so we've got this side. Now, we're almost there to get the R. We need this length here, right? And so in order to do that, what we need to find is, well, we know we went 6 meters down, but we went straight back up right away, but only the y component of this. And so we need to find y1. And so in order to do that, we're going to do that over here. Find y1 equals, it's purple, sorry. All right, y1 equals, what is y1 going to be? It is going to be cos of 32. So look at your question, and what you'll see is we know the adjacent and the hypotenuse, and so we're going to use cos. And if we do this, we're going to get the same kind of setup. It's 4.0 cos of 32 equals y1. And then we get the answer to be 3.4. So y1 equals 3.4 meters. Very good. Which means that this component here is y1 is going to be 6.0 minus, because that was down, and then we went up 3.4. And so we get a total of, that will equal 2.6 meters down. Okay, and so if we redraw this triangle, this is the resultant. This is all we care about in the light blue here. So let's draw this out, and I'm going to draw it in green because light blue is too hard to see. And so what we found so far is that we went, a bit red, we went not 3 meters, because 3 minus 2.1, we went 0.9 meters this way. And then down, we went 2.6 meters. And so we've got to find this distance and this angle. Okay, so what we did is we figured out, put all of our vectors together, and that helped us to determine how to figure out our side lengths. Now we got our side lengths, and now we scrap all of this. Okay, that part is done, and now all we're focusing on is this part. Okay, because this is really where we went. We started here, and we ended here, and the length there, R, is this length here. Okay, we're redrawing this blue triangle here, and so this is how far we really went, because we didn't need to go all the way down here if we just wanted to get from here to here. And so that's what we're testing. That's what it means to add vectors, because we cancel out things that were opposites. And so the way we do that is r squared equals 2.6 squared plus 0.9 squared, and you get r value of r equals, and here we would do like the square root of what's 2.6 squared plus 0.9 squared is 7.57. And then what we do is the square root of 7.57 is 2.75, so that's 2.8. Okay, so r equals 2.8 meters. That's awesome. So we're done, almost. We've got r, but we still need theta. And it's very tempting to quit once you've got r, but you're not done. We need theta. And the way that we get theta is, well, what do we know here? We know the adjacent side and we know the opposite side. So we're going to use tan. And this is often how it's going to go. And so tan of our angle is going to equal the opposite, which is 2.6, over the adjacent, which is 0.9. And if we do that, we get, well, to get rid of the tan, we got to do theta equals, and it'll be tan to the minus 1 of 2.6 over 0.9. We got that. Okay, so this is how you get rid of the tan. You got tan theta of a fraction. You can go theta equals tan negative 1 of that fraction, right? You move it over by using the negative 1. So go inverse tan of 2.6 over 0.9, and you get 71. Theta equals 71 degrees. Let's do that here. Equals 71 degrees. How do you write your final answer? Your final answer is going to be 2.8 meters, square bracket, 71 degree. And then what is this degree? Well, we started, our dotted line here is to the west, and we went south of that dotted line, and so it'll be southwest. Like that, close the square bracket, 2.8 meters, 71 degrees south of west. That is the resultant vector. That is what we get if we add up all of these vectors. This is a super tough question. It's a big question. And this is how we do it. We got to add up all the components. We figured out exactly how far east-west we went, how far north-south we went, made a new triangle, and then found the resultant vector there with the angle. And there we go. Pretty simple. It's pretty tough stuff. What you might have to do, another way of doing it is to use the scale diagram, and I'm supposed to teach you how to do this. So let's figure out how to use a scale diagram. For this, you need a protractor and you need a ruler. So all you got to do is pull one of them up, just like this. Boom, magic. There it is. And so what we're going to do is we're going to draw these to scale. And so you can't draw 200 meters on here, but what you got to do is say one cell is, I don't know, 25 meters. Okay, 25 meters. Okay, that's how you make it to scale. Or in this case, if you look at my ruler here, 1 centimeter is 1 cell. And so I could write here, 1 centimeter equals 25 meters. Okay, and so if we're going to do that, then I can draw my first line pretty easily. I set up my ruler. I can't actually turn this ruler, so it's stuck flat like this, so it's actually totally useless to me. But I'll say this is my starting point right here. Why would I choose this point? Because I can look. I'm going to go north, and then I'm going to go northeast. So if I start here, I'll have as much room as possible. So I'm going to go 200 meters north. Well, one cell is 25 meters, so I've got to go 8 cells. And so I go start here, and I go 1, 2, 3, 4, 5, 6, 7, 8. I lost count. I don't know if this is right. 4, 8. Yeah, looks good. There you go. Make it perfectly straight. Use your ruler. Boom. It's got to be perfect, okay? Because we're measuring this stuff later on. And so as you can see, mine is not, but it doesn't matter because I'm not the student. No, I'm just kidding. All right, there we go. Bang on. We've got a 200-meter line that's represented by 8 centimeters. Now we've got to do 300 meters, 30 degrees north of east. Well, how do we do that? We set up a protractor. Okay, and I'll show you how to use a protractor. You need one of these. If you don't have one, I've got one at school. So then you'll need to borrow one from me, but this I need you to do. Okay, I need you to learn how to use a protractor. So what you do is you line up to make sure this is perfectly horizontal here. So that the 180, do you see this line here? Okay, this line, horizontal line, it's got to go right into this 180, and the protractor's got to just keep going parallel with that line right on top of it so that you know it is perfectly set up. This line here needs to go right through the 90 degrees, so I could probably shift it over just a bit right there. And so it's going right through, so it is just perfectly set up so that this dot is right on the edge of the line, okay? And that is perfectly flat and level. And then we mark out, this is what you would do, is you'd use a pen and you'd mark out 30 degrees north of east. So this is east here, and we've got to go 30 degrees towards the north. And so we count from the 0 in this line. Here's the 0 here. And so we go 30 degrees to the north, 10, 20, 30. And then we make a tick right there at the point that is 30 degrees north of east. There it is. Okay, and once we've done that, we can take our protractor, move it out of the way, and then we get our ruler and we line it up. Now, if I could turn my ruler, that would be fantastic, but I can't. And so you got to turn your ruler so that it is connected here, boom, with that 0 perfectly lined up. And then you tilt it so that it's going from this point through this point. Okay, and then you measure exactly. This was 8 centimeters to do 200 meters, and we're going to need 12 centimeters to do 300 meters, right? Because every 4 centimeters is 100. And so then you measure exactly 12 centimeters. All right, so here, it'll be somewhere up here. My line's not going to be perfect, but yours is, because you're going to use a ruler and you're going to measure it. And so then you insert a line. Oops. And this line has to be exactly, like we said, 12 centimeters to represent 300 meters. And has to start exactly at that tip. And then it's got to go right over that dot. So 12 centimeters would be right about there. I don't know, I'm just guessing. But it's got to go right through that line. Okay? Boom. And let's make sure you measure this as 12 centimeters so it represents 300 meters. And so what we've got now is this beautiful line that started here, went up here. This is the first vector, and we added it to the second vector. And as you can see, this is a lot of work to get it, and it's just not quite as accurate, but it is pretty accurate if you take your time. And we should be within 1 decimal place, okay, if we did our measurements well. And how do we figure out what our final velocity was? Remember, we're adding these two vectors. So what we do to get our final velocity, or sorry, final displacement, is we draw a line starting from the start and going straight to the finish. So right from there to there. All right. And this, then you measure it. So I have no idea. I can't use my ruler, but you measure it. And so say that it is 15 centimeters. Oh my goodness, using lines. Say that it is 15 centimeters. Then you think, oh, wait a minute. 1 centimeter is 25 meters. Okay, so then 15 times 25 would give would give us 375 meters. So we would predict this to be 375 meters. Okay, maybe 380, 2 sig figs, right? But hopefully you can measure this to 15. Let's do 15. Oh, I can't change it. 15.0. I'm gonna erase this because you should be able to measure pretty accurately. So you should be able to say this is 15.0 centimeters, and then we did times 25 meters for every 1 centimeter, right? And the centimeters cancel, and we get 375 meters would be our final. So I don't know what you measured. You'll get a better measurement than me, right? But we'd also need an angle, right? And so the way we do that is we pull our protractor back down and we line it up just so it lines up. Notice how the bottoms are right onto that middle corner is where the intersection is. The green line goes right through the 90. It is just perfectly lined up. And then we measure this angle. And my angle will not be as good as yours, but my angle looks here to be 124.5. Like it's right in the middle. So 124.5, but that's not a good angle. So that's really 10, 20, 34.5. And so to finish this off, we go 375 meters, 34.5 degrees. Oh, I should do here 34.5 degrees. This would be east of north, right? And so there it is. That's how you do a scale diagram. It is different. than doing all the math. It is less accurate than doing the math. It is probably more work than doing the math once you get good at the math, but it's a way of doing it. All right. And so that's that. So I'll do a few more questions with you. This is review from last year about acceleration. A bird is soaring down to the ground with a constant vertical descent of 12 meters per second. How far will the bird drop in 7 seconds? Got two things. The velocity is 12 meters per second. We have the time is 7 seconds, 7.0 seconds. And if you remember our formula, it was this: A equals V over T. Oh, we're not doing acceleration. Jeepers. Let's try again. V equals D over T. Why do I ever use this? So bad. All right, let's do the equation. Our formula is V equals D over T. Like that. And so we don't know D, but if we multiply both sides by T, we end up getting the formula D equals VT, right? If we multiply both sides by T. So this is the formula we're going to use. You can use a triangle to get that as well. And so we punch it in, D equals 12 meters per second times 7 seconds. And you get an answer of 84 meters. Negative's not bad, but all right, there you go. It'll drop 84 meters. The cheetah gets to its top velocity 32 meters per second in 3.8 seconds. Okay, so we got 32 meters per second. That's our velocity. It gets up to that, and so it seems like it changed that much in a time of 3.8 seconds. What is the cheetah's acceleration? Well, our formula is A equals V over T, and that's the change in velocity, and it seems like it changed 32 meters per second because it got up to that, so probably from rest. So then our acceleration is 32 divided by 3.8, and we get that becomes 8.4, and this was meters per second, and the way I like to do that is 8.4 meters per second squared. Whoa, something happened there. I should have been looking up. Equals 8.4 meters per second squared. That's how I like to do it. Very good. Diving golden eagle. Hopefully that's familiar. What's the velocity of the eagle if it travels 187 meters? Okay, that's a distance there. Distance equals 187 meters in a time of 2.8 seconds. Well, here's how we do it. Velocity equals distance over time. And so we gotta just plug it straight in. So velocity equals 187 over 2.8. And we get 7 over 2.8. 66.7, so 267 meters per second. It then slows down at a rate of 8.3 meters per second squared. That's an acceleration. Write that down. A equals 8.3, and it's negative because we're slowing down, right? Negative 8.3 meters per second squared. As soon as you see meters per second squared, you know it's an acceleration. How long does it take for the eagle to stop? So we know V1 was 67, V2 was negative 67, so our change in V is going to be negative 67. We want it to slow down 67 meters per second, and we want the time, right? And so we know our formula is A equals delta V over T, but we want T, and so we swap T and A, so we get T equals delta V over A. That's what our formula is going to be that we're going to use. So we plug that in, and we get T equals delta V, in this case, was negative 67, divided by A, which was negative 8.3, and we get an answer of 7 over 8.3 gives us 8.1 seconds. This is seconds because meters per second squared, the time is going to be seconds. There we go. So that's it. Hopefully that was all fun. It was a blast for me. I'm glad that we were able to do this. All right. Have a good rest of your day, and I'll see you tomorrow. Tomorrow we'll probably just have a worksheet and we'll start working on this. Very good.